is from your experimental work, you found out that there's a relationship between the kinetic energy and the potential energy, and also you've got equations that relate the velocity of a particle with simple harmonic motion, that relates it to its displacement. So it's really still tied in with energy in simple harmonic motion that we're dealing here. Think first of all about the kinetic energy, because you've got an equation for kinetic energy. The graph that you've just plotted, if you take the zero displacement, the displacement there, what you were finding is you get maximum kinetic energy as it passes through the center, which makes sense. And then it comes down either side there. Mathematically, what shape was the curve? You checked it. Okay, so you've got a parabolic curve going up and down, very similar to the curve that would be if you threw a ball or something, go up, and would come down in a sort of inverted parabola. And if you look back in your notes, what is the equation for velocity of the simple harmonic motion particle in terms of the displacement? Got a page or two back in your notes. Okay, plus or minus omega, square root of a squared minus y squared. So actually we're using y for displacement rather than x. There. Why is it plus or minus mathematically from what you did in terms of deriving that? You got the derivation of it by using sine squared plus cos squared equals 1. Okay, so you take a square root, so you've got to be plus or minus. In terms of physics, why does that plus or minus actually make good sense here? Yeah, so the plus or minus is saying that the velocity of something is going up or down depending on where the displacement is. You'll get positive or negative velocity. The kinetic energy, though, in common with all energy, is just positive. So how are we going to get to an equation for kinetic energy in terms of displacement y using that? And it's not that difficult. You could differentiate it, but if we're after energy in terms of speed, that doesn't require anything to be done with respect to time. Everything's happening with respect to displacement. You've got an equation for velocity. We want an equation for kinetic energy. We've got a mass that's bumping up and down. Chris? Right? Yeah. So we're going to use just dk is half mv squared. And so we've got v is that lot there. So we've got half of m. The plus or minus doesn't matter because we're going to square that. Omega becomes omega squared. And the plus or minus the square root of a squared minus y squared is just a squared minus y squared. So that is your equation for kinetic energy for a particle of mass m, pulsatance omega, with amplitude a at any particular displacement. So we can dial up any displacement on the graph here and work out what its kinetic energy is using that equation there. Thank you, Anna. Okay, so it is a squared minus y squared from your notes, yes. Okay. So you've got this kinetic energy here. We said that the potential energy is just the total energy minus the kinetic energy. So you've got this graph here for potential energy, and that was your graph for kinetic energy. That's what we've just seen on the results. How can we get that graph, that relationship for potential energy with that one there? We could go through a similar process. What's the maximum possible kinetic energy from that equation there? When will the kinetic energy be at a maximum? And y is 0. So if we put y is equal to 0 in here, the kinetic energy maximum, it sounds like a good brand for soft drinks or a sort of mountain bike or something, max kinetic energy or max EK or something like that, but it's just what we're after at the moment. So you've got maximum kinetic energy, half m omega squared a squared. That's kind of comforting if you've been following these equations. You don't look comforted. Because the equation that you've got for maximum velocity, Vmax, which sounds more like a brand of estate agents, Vmax, what's the equation for maximum velocity for something undergoing simple harmonic motion? A omega, okay? So the maximum kinetic energy is going to be the half m times the maximum kinetic energy squared, a squared, omega squared. So it works. All right, that's our maximum kinetic energy, so that's maximum EK. To get the potential energy is going to be that maximum EK minus this here, minus the kinetic energy at any point. So that's actually going to be half of m omega squared a squared minus a half of m omega squared a squared minus y squared. I think I've got all the right squareds and halves and m's and omegas in there. What does that leave you with at the end of it? Apart from alphabet soup. Well, you could do that half m omega squared a squared. If you expand that bracket, you've got half m omega squared a squared minus half m omega squared y squared. So that minus that first term would be what? Yeah, because that knocks out that. So you're just left with minus half m omega squared y squared, which is a parabolic shaped graph in the form that y equals 4ax squared, you might know from maths. What we've got here is potential energy is a parabola proportional to y squared. So that's one degree of comfort in this, that we've got a parabolic equation for the potential energy. The second thing which makes it sort of quite comforting is if you take the example of a spring. This is just sort of finishing off here. For the example of a spring, what's the omega factor if you've got a spring system? If you look back in your notes, you should find out with a spring and a mass system, what's omega equal to? Omega squared is k over m. K was the spring constant particular to the spring, m was the mass. Ringing any kind of bells or even sort of oscillating at all this? Yeah. Okay, so for a spring and mass system, omega squared is k over m. If we put that into this equation here, you're going to end up with the potential energy is half m k over m times y squared. Mass cancels, so the potential energy is equal to half k y squared. And in terms of a spring on a mass, that again is good news, because if you plot the force against the displacement for a spring, what shape does that force against displacement graph look like for a spring? We're kind of recapping a lot of the things you've done now. Okay, so you get a negative slope there, like that. So you had F is equal to minus ky, whereas what you had for that there. The work that's done, the energy in taking the spring from there to there, how do you calculate the work or the energy in pulling a spring a particular distance? force times distance. So it's the force times the displacement, but just, and similar to many things that you've done in physics, the force isn't constant. It's proportional to distance. So how do you get the energy or the work done in extending a spring out to displacement y using that graph? Because the two are proportional. So you could take the area under the graph because it's a varying force with displacement. So the area of the graph it would be equal to the work done, which will be the average force times distance. So the energy, the potential energy in stretching out a spring, that force over that distance, what will that be in terms of the graph here? You've got half of F times Y, which is the area of the graph, half the base times the height, half F times Y. What's the force equal to in terms of Y and K? So it's equal to minus a half K times Y, because that's the force, K times Y. So the potential energy is a half K Y squared, which ties in very nicely to what we had just there. So we're seeing the thing from two different ways. The good news, the negative went because it's an energy, and with energy it's a scalar, so we're not interested in whether it's positive or negative. Okay? All that the negative is saying is, are you actually applying energy, or is there energy released? Is it positive or negative work done, which we'll come back to in gravitation. So we've got potential energy is half ky squared. The good news is, so you would not be expected to need to do that for advanced higher. I'm just showing you how it does tie in. But what you would need to be able to do is this bit here, to be able to get the kinetic energy equal to half m omega squared a squared minus y squared, and the potential energy is half m omega squared y squared. Those two equations you do need.